Okay, welcome to Thinking Beyond. Before we get started, I just wanted to remind everyone of our upcoming Beyond the Annual Lecture with Brian Greene. For those of you who are local, it's on March 14th at 7 p.m. and you can register at links.asu.edu/beyond 2024. And then our next Thinking Beyond will be on March 25th, and that will be with John Maddock, and it is on the dark matter in our genome. Registration will open mid-March for that, and I will send out links via email and social media, just like usual. And then for tonight's webinar, if you have any questions during the presentation at any time, you can submit them using the Q&A feature at the bottom of your screen, and then we will get to those towards the end of the hour. So that is all I have. So I'll go ahead and turn it over to Maulik Parikh, who will be moderating for tonight.
Yes, hello, and welcome to tonight's Thinking Beyond webinar. So the topic of today's webinar is quantum measurement. And quantum measurement, as most of you may have heard, is this problem that has bedeviled us for close to a century, and it's essentially about how to reconcile the sort of definite world that we observe around us of classical mechanics and of measurement with the hazy probabilistic underpinnings of quantum mechanics. And it's a problem that people have been thinking about for a century. And we're very happy today to have Professor Andrew Jordan telling us about it. And he is an expert on the subject. He has thought very deeply. In fact, he's literally written a book on it, which you can see on the screen right now. So this is a serious textbook, but he's going to today describe his it in terms that are more widely accessible. But just as a bit of background, Professor Jordan received his PhD in theoretical physics from the University of California in Santa Barbara. And then after postdoctoral stints at the University of Geneva and at Texas A&M, he joined the University of Rochester, where he spent many, many years. And more recently in 2021, he joined Chapman University, where he serves as a co-director of the Institute for Quantum Studies. And he will be joined today by Professor Paul Davies, whom you all know very well from previous Beyond Thinking Beyond webinars. He's, of course, the professor of physics here, the director of the Beyond Center for Fundamental Concepts in Science and ASU Regents Professor. And he too is thinks a lot about quantum mechanics. In fact, he's writing a book on it as well. And I had a discussion with him this very afternoon on quantum cosmology. So without any further ado, let me pass it on to Professor Jordan for his presentation. And again, if you have any questions, please enter them into the chat and we'll get to them at the end of the seminar.
Okay, thank you, Maulik, so much for the very kind introduction. I wanted just to begin by thanking you and Professor Davies for kindly inviting me on this webinar. And thanks to all of our listeners for taking the time to come and tune in. I'm happy to discuss with you and talk about quantum physics with you. And so indeed, as was just announced, I'm very thrilled. I just got, like yesterday, the first print copies of my book. So I'm very excited about that. And I'll be telling you about that today. And I want to use the book as an outline to kind of guide you through some of the really interesting phenomena about quantum measurement. I love this field because it involves so many different things that I'm really fascinated by. So it involves hard science, so empirical tests of reality. It involves our construction of mathematical formalism to try to understand and predict and find the patterns in that phenomena. But it also involves really interesting philosophical questions that help to inform our view of the quantum world and to help refine our understanding about what these objects that appear in our quantum formulation are all about. So the plan, I just thought with Paul, I'd take maybe 20 minutes to guide you through some of the things in my book as an outline, and At that point, we can go into some of the in further depth into your questions, and I can answer as best I can. But also the great thing about this field is that we don't have everything figured out. There's a lot, it's an unfinished story, and so there's more to be done, and so that's also exciting for me as a scientist. So let me start by pulling up my slides here. Okay. Now I have to ask the obligatory question. Can you see my slides? Yes, Paul is nodding. Excellent. All right. So this is the outline of the talk I want to give today. I'm going to tell you about, first of all, a little bit about where I am. Maybe not everyone is familiar with Chapman University as you're familiar with Arizona. I'll talk a little bit about what I do, what I work on when I'm not writing textbooks. And then I'll go through some of the details of my book. And then I'm going to stop after I go through the book, but I have more stuff about some reviews from different scientists I could talk about, or an interesting story about art and science, about the design of the cover. I could talk about that if you're interested, but I'll leave that up to you. So first of all, where is Chapman? So I live in Southern California. It's outside of Los Angeles in Orange County, in the city of Orange, just north of Irvine. You see that in the little map dot. I live down where the little hearts are in Laguna Beach, and Paul has visited me at my home, and I got to show him around this beautiful beach town where I'm lucky enough to live. And I love Chapman. It's a private university. It's very different from my former institution, the University of Rochester in New York. For one thing, I joke that I went from the worst weather in the country to the best weather in the country. But aside from that, there are many nice things about the university as well. So what do I work on? So my interests are things like quantum measurement and control. So how do you make quantum measurements, and then how do you control quantum systems? Things like using quantum mechanics to make very precise measurements. So this is called quantum metrology. So can we use advantages of quantum physics to do better measurements than you could with classical physics, for example? I work on topics involving quantum thermodynamics, something that's near and dear to Paul Davies' heart as well. This topic of trying to miniaturize the laws of thermodynamics and figure out the smallest heat engines, how to design thermoelectric engines in semiconductor structures, for example, how to build miniature quantum-driven engines. And then the topics of, for example, the foundations of quantum mechanics, things like weak values and weak measurements, the nature of time, things that I think the viewers of this program will also find very interesting. So that's a kind of little overview about my research interests. And here is the book. So this is published by the Cambridge University Press, and my co-author is an experimental physicist, Irfan Siddiqi. So I am a theoretical physicist. Irfan is a experimental physicist. And so two of us together made quantum measurement theory and practice. And what I love about the book is that we were able to bring these two things together in a seamless way and be able to write about quantum mechanics, integrating in the best knowledge from both of these points of view in really a seamless way. So if you read the book, you can't tell, this is the part Andrew wrote, this is the part Irfan wrote. No, it's really very well integrated, in my opinion. And so Irfan leads a really big lab in University of California, Berkeley, in the northern part of the state. He's really one of the world's leading experimental physicists. So it was a great pleasure to write this book with him. I just thought, just for the curiosity's sake, here's the timeline of the book. When you read a book, pick up a book, you don't realize how much goes into it. So I'm not going to go through all of these things, but it started back in maybe spring of 2019. Some colleagues urged us to write a book. My friend Irfan said, we should write a book. And COVID was a horrible thing, but one of the good things it did is it locked me in my house. I couldn't do anything except sit and write. And so a lot of the book was actually written during the COVID period when I was still at the University of Rochester in the winter, where it was just lots of snow and you didn't want to go do anything except type on your computer. So anyway, I ended up moving to Chapman in the summer of 2021, and the book just got published a few days ago. So this is really cutting edge stuff. You're getting right from the source. So that's the timeline of the book. Here is a picture of Irfan and I celebrating where I live in Laguna Beach. This was around 2021, or 2022, I guess, and we thought we were done, but then it takes a long time to get proofs and editing and your friends commenting on you should do that. Anyways, so we're going to celebrate again here very soon. So here's what the book is about. It's divided into three basic subjects. One is what we call fundamental principles. So these are the things that are really core. The second is advanced topics. And the third is applications and implementations. And what's interesting is that there's something really for everyone in this book, because chapter 1 and chapter 11, the introductory chapter and the concluding chapter, the epilogue, are written in English. So anyone can read what's in there without having any kind of advanced training in mathematics or physics and be able to get something out of that. And so I'm planning on giving copies to my relatives and friends. And so you too can even if don't have a lot of technical training, you can learn about the history of the field, the overview, what we think are the most important questions, both from a scientific and philosophical question from this outline. And just to kind of whet your appetite, what are some of the questions we deal with? So I've listed a few of them here to intrigue you. So one question would be, what we've learned about quantum measurements is they can take time. How long does a measurement take? Can a measurement be reversed? Is it possible to track wave function collapse? How can you entangle objects that are separated spatially by measurement? When does a state jump versus diffuse? What's the most likely path of a quantum trajectory? How can you describe joint unitary and non-unitary processes? And what limits does quantum mechanics put on amplification? And how does one build a quantum limited amplifier? So those are some of the questions that get answered in this book. And so if those intrigue you, the book will teach you all about it. And I'll start to cover some of those here for today's presentation. So the overall subject matter is given here. I give some pictures on the right-hand side. The first is the wave function represented by the capital Greek letter psi, and it has the property that collapses. So it collapses on its side, and we want to learn what's this wave function collapse stuff all about. The famous feline that Erwin Schrödinger, the great Austrian physicist, introduced, Schrödinger's cat paradox, that's penetrated into our popular culture. On the right-hand side, you see the wave functions depicted of the hydrogen atom. All these things are part and parcel of the quantum story, and we get into that. So one of the things that we try to do in this book is we try to tease apart things that are often conflated: philosophical issues, mathematical issues, physical issues. What we do is we give a physics-first approach to quantum measurement. So every chapter begins with a motivating experiment. This is something that happens in reality. This is something that exists in our experimentation. In seeing that pattern, trying to understand what's the pattern behind that. And only once we understand that and describe the physical instruments that are used, do we begin to start uncovering what are the mathematical methods that are used, what are some of the then only then, after we have the mathematical formulation, the experimentation, the understanding, the predictions, do we then get into some of the what is the philosophical aspects that this implies. Well, that's the overview of the book. And then I'll just mention some of the cardinal properties. If you read about textbook quantum measurements, when you make a quantum measurement, you learn something about a quantum property, and then what you have to do is you have to take the wave function that described it and then replace it with something else. So these are the properties of quantum measurements. They're projective. They collapse into a particular state corresponding to the observed property you measure. They're irreversible. You cannot undo them according to the lore of quantum physics. And John Wheeler poetically captures this, paraphrasing Niels Bohr, the great Danish physicist. We are dealing with an event that makes itself known by an irreversible act of amplification, by an indelible record, an act of registration. So you can't undo an indelible record, or can you? We're going to get into that. And then finally, it's instantaneous. This happens all at once. And Heisenberg points this out, that he talks about an idea where a reflected wave function, the wave packet exists in a distributed sense in all of space. And by measuring a particle in one space, it immediately eliminates the wave packet in the other part of the space. in that speed at which that happens can be made as fast as you want. So they said to be instantaneous. So these are the kinds of things you learn about in textbook quantum mechanics. But we've learned so much since the time of the founders back in the 1920s, 1930s. And one of the great things we've learned about are new kinds of measurements you can make. Sometimes these are called generalized, weak, or continuous measurements. And the exciting is that these can break all three of these properties. They can be take place over a period of time, they can be probabilistically reversed, and they can be minimally disturbing. So the book goes into great detail about all of these new discoveries that have been experimentally verified. And then just giving a quite quick summary, we start with an opening chapter of reviewing the founders of the field back in the 1920s with Niels Bohr, going through the equation of Schrödinger, the principle of Heisenberg, the complementary principle of Bohr, and then into the era of John Bell, trying to probe further the nature of reality. Does quantum mechanics describe reality or only our knowledge about reality? And then we go into some basic concepts about reviewing some basic properties of quantum mechanics. Where the word quantum comes from? It comes from the fact that what we thought to be continuous in the classical world becomes a discrete variables, and then goes on into things like what happens when I do a measurement. And some very surprising things can count as a measurement. For example, when something doesn't happen, that can collapse the wave function. And so what the example we give is the famous exchange between Arthur Conan Doyle's character Sherlock Holmes and the Scotland Yard and the Scotland Yard detective Gregory, about the famous incident of the dog that did not bark. So the fact that dog does not bark gives you information about what happened. The same kind of thing happens in quantum physics as well. Talking about topics like weak values, my co-author, my co-director here at Chapman University that Paul Davies knows very well, Yakir Aronoff, helped discover an interesting effect called the weak value. And so I've been involved in some of the research putting that effect to make very precise measurements, and I cover those experiments in the book as well. We go on into more advanced topics like superconducting circuits. So one of the most exciting things in the quest to build quantum technologies, building off of our knowledge, one of the great quests is to build a quantum computer using quantum principles to do computation. And one of the best architectures for that is what happens if you take, for example, a piece of aluminum and you make a junction with another piece of aluminum and some oxide in between. That becomes the building block of a new kind of quantum circuit, the so-called Josephson junction quantum circuits. And so my friend Irfan Siddiqi, my co-author, builds these chips that you see like so, that have very nice controllability, that maintain their quantum properties. They're put at the bottom of a very, very cold dilution refrigerator at millikelvin temperatures, a thousandth of a degree below Kelvin, 1 Kelvin. And we discuss the technology behind building those circuits. And then once you have them, what can you do with them? One of the great things we can do is this concept of wave function collapse actually can become a continuous process. So we can actually monitor how the wave function is collapsing as we're monitoring the quantum system, and be able to track that wave function, and even in a single run of the experiment. That's really exciting new discoveries we've been able to make. So we said the wave function collapse is no longer some mysterious black box thing to be discussed only in philosophy, but an empirical process that can be characterized and tested extensively in the laboratory. Okay, and then we talk about how do you do things like build quantum amplifiers. If you're going to do measurements, you have to do amplification. Quantum mechanics puts limits on those amplifiers, and we talk about those limits and what kind of noise sources quantum mechanics demands if you take a sort of weak signal and are able to amplify it up to a strong signal. But once you have that fundamental limit, that's not enough. You have to actually then go into the lab and build these amplifiers. And that's something that my co-author is really an expert at, is putting together all these quantum circuits that are able to do that in a quantum efficient way, so you don't lose any quantum information, or you lose the least amount of information possible as you scale up the signals to classical signals you can read out on your oscilloscope in your laboratory. So we go into how to design those as well. And then we talk about measurement-related phenomena. A very fascinating example is something we call quantum uncollapse. So if you partially collapse the wave function, it turns out that it's possible to undo that. So that contradicts that first cardinal principle of quantum measurement, the fact that it's possible to reverse a quantum measurement under certain circumstances. And I can talk more about that later if you have questions. And then another concept we talk about is the so-called most likely path. So as the quantum system collapses on a continuous trajectory, what's the most likely way it goes to get from point A to point B? We'll talk about that as well. One of the other really fascinating things, if you know about quantum mechanics, you know about the Heisenberg uncertainty principle. And that says that the uncertainty in position times the uncertainty of momentum of a particle must be bigger than or equal to a fundamental constant, the reduced Planck's constant. That's really a qualitatively new feature of quantum mechanics. And the fascinating thing we've been able to discover recently is that, in fact, you can make joint measurements of momentum and position. But as you do that, as you measure momentum more precisely, you must scramble the information about the position and vice versa. And that has actually been done now in the experimental laboratory. And the way they do that is with this little circuit drawn below. You have one of those superconducting circuits I mentioned. And then what you do is you use two different modes of the cavity to read out the two different complementary observables, analogous to position and momentum. We can do things like feedback control, and this is an example of using error correction in this circuit. And the error correction allows you to preserve quantum information, but be able to only measure the errors that happen in a quantum process. And we have ways of being able to continuously implement this quantum error correction protocol using these quantum circuits. Talk about that as well. And then finally, at the end, we switch. Up till now, everything has been super strict science. This is what we know based on evidence, based on mathematical formalism. But then we sort of switch gears and talk about philosophy. And the epilogue is titled, "What Does It All Mean?" And maybe you'll be disappointed, but maybe you'll be relieved to know that we don't really know the answer. We have many hints. So one of the things that we conclude, there are different interpretations. One of the things we think that the information or that the results are pointing to us to is the fact that, in our opinion anyway, that the wave function is not something that exists out in reality, but rather it's our description of the quantum system. So the wave function collapse is not an external thing, it's simply an internal thing, much like what happens when we update a probability distribution if you were a statistician. Okay, that explains many of the puzzling facts, but it's not entirely satisfying. There are many outstanding issues as well. And our conclusion about the many interpretations of quantum mechanics is what we like to say is that the best interpretation is a fruitful interpretation. So if it leads you to new discoveries and predictions about reality, or what our experiments of reality anyway would be, that is wonderful. And so that's, I think I'm going to stop there, and I can continue to go, but I want to take some of your questions and we can have a discussion as well.
So, Maulik, can I chip in at this stage?
Yes, go ahead, Paul.
Well, look, thank you, Andrew. You covered so many topics, it's hard to know where to begin, but to pick one at random, because Maulik and I happened to be talking about it just today, the uncertainty principle, what does it mean? And you, in a somewhat throwaway manner, you said, well, we don't, it is possible to measure these complementary things simultaneously, which was a teasing comment, because I'm bound to ask, well, if you do it again, will you get the same results next time? And there must be a price to pay for attempting to circumvent this fundamental law.
Great question, Paul. So when I was a student learning quantum mechanics, they just told me it's impossible to jointly measure momentum and position. Full stop. But we've learned that that's not true. Okay, so let me unpack what the Heisenberg uncertainty principle is. Really, it's a mathematical statement. It says if I take a wave function, okay, and I take the dispersion and I measure, and that represents a particle, and I make a measurement, where is the particle? And I do this over and over again with the same initial conditions, I get some spread in the position of the particle. Now, if I said I did some other experiments, and I measured again and again the momentum, I would get some spread of the momentum of the particle. And so all the Heisenberg uncertainty principle tells you is the product of those uncertainties is bigger than or equal to h bar over 2 at best. Okay. Now, what it doesn't tell you about what happens if I try to measure position and momentum at the same time. Okay. And so what we find is that we can do that in the laboratory now. We don't do a position and momentum of a particle. What we do is we use basically a pseudo spin, which is a 2-level effective degree of freedom, and we weekly measure, continuously measure the for example, the X operator, like the one component of the spin, and then a non-commuting component of the spin, like the Z operator. And what you find is that you can tune the strength of those two measurements. You've got two handles on this device now. I can measure this guy or this guy. They don't commute with each other. And what you find, that trade-off you were referring to, Paul, is that the stronger I make this measurement, the quantum states tend to collapse upon the eigenstates of this observable. On the other hand, if I try to make this measurement very strong, the wave function tends to collapse along the eigenstates of this measurement. And you can say, what happens if I measure them both equally strong? And what happens there is that no collapse happens at all. So upon measurement, you're measuring like crazy, system doesn't collapse. What happens, it just diffuses on its state space. It becomes a random walk with no preferential collapse direction.
Ah,
So you're projecting onto the eigenvalues of xp plus px, not to get technical, but it's a, I mean, that's the Hermitian operator, right?
Yes. Yeah. To be technical, it's a spin 1/2 system. So I'm weekly measuring say sigma poly Z and poly X, for example, jointly. Yeah.
Well, to go from technical to philosophical, because I think a lot of people following us will be intrigued to know about about the nature of reality and what quantum mechanics can tell us about that. And so if we just go back to basics, I think it's pretty well known that Einstein was very uncomfortable about the whole of quantum mechanics, and he used to have these conversations with Niels Bohr about what does it all mean and so on. At the risk of oversimplifying, the Einstein tradition, which is that there's something missing from quantum mechanics, is that beneath this quantum world, with all its uncertainty and weirdness, lies a classical world, a world much more like the physics that you learn at high school, if people still learn physics at high school, and the discussion as to whether or not there can be so-called hidden variables that are at work underneath a quantum system went on for decades and decades. But throughout my career, it seemed to me that really very few people are prepared to sustain the idea that there is these hidden variables at work underneath the quantum world. And I'd just like your opinion on that. You're at the cutting edge of this. You collaborate with somebody who actually does experiments. And of course, it's often said that the response to these philosophical problems is shut up and calculate, because it doesn't actually affect the results you get in quantum mechanics, and certainly doesn't affect what happens in the lab. But nevertheless, you presumably have a position. So, are there hidden variables underneath it all? Or do we just accept the weirdness of quantum mechanics as that's the way the world is?
So that's a great question, Paul. And in fact, we go to great lengths into this discussion in chapter 1. So we trace the history of this, starting with the Bohr-Einstein debates. And not only Einstein was very unhappy with this, but Schrödinger himself was very unhappy. That's actually why he invented the cat paradox, because he hated these probabilities. His quote, famously quoted as saying, "I don't like it. I wish I never had anything to do with it," because he was hoping that by solving some wave equations, just like we could for water or for air, that solves everything. Okay. And only later do people begin to realize, aha, no, this is some kind of probabilistic stuff, and I don't get the definitive result. And when I measure this, I get some spread of results. And this is one of the things we talk about in the book. No matter how simple the system you get, no matter how carefully you prepare the system, identically prepared systems give rise to different final results. And that is really the revolutionary property of quantum mechanics. Now, getting back to your point, Paul, about Einstein's hope. So we go through this in chapter 1 in great detail. What about hidden variables? Or so von Neumann called them hidden parameters originally. Bohm took up this notion of called it hidden variables. And so we talk about the role of Bohm in this story and the fact that he could create some alternative interpretation of quantum mechanics, the so-called de Broglie-Bohm, building off of earlier ideas of Madelung in the hydrodynamic formulation of quantum mechanics, but also de Broglie as well, to create this alternative formulation. And we go through that history and then go into what we call the era of Bell. So we have the era of the founders, we have the era of Bell, we have the classic experiments, and then we have what we call the quantum information era. So really in the era of Bell is what you're talking about, is this idea that can we test this notion of hidden variables? Because indeed, many of the very great physicists struggled with this idea. And to this day, a huge industry in quantum philosophy, basically our philosophers are saying this simply can't be true. It simply can't be the case that there's no reality. We must have something wrong at a very deep level. And so what Bell did was something very important, is that he published an inequality. We cover this again in great detail in chapter 1, that sets up a conflict, a scientific conflict between the notion of hidden variables under certain assumptions and scientific experimentation. And basically the conflict is that if that situation you outlined that were true, that there were some underlying hidden variables. And the analogy I make that I make to this situation is like statistical mechanics. Statistical mechanics describes some collective behavior like temperature, entropy, things like that, from microscopic degrees of freedom, particles, spins, things like that, and applying Boltzmannian principles to be able to predict the macroscopic properties from the microscopic properties. And so I think the hope of Einstein was maybe there's something more fundamental than these particles we're seeing, or that we just simply can't see. And that if we had a proper theory of those things, then it would restore our notion of classical reality. And what Bell showed is that using his situation that we describe, I won't go into the details of it, but what he showed is that based on the experiments that were done, the fact that his inequality was violated, that it shows that can't be true without breaking some of those fundamental assumptions of his inequality. Okay, and so different people take different reactions to that. So maybe to stop this and go to the epilogue of the book, we make a prediction there, Paul, and this answers your question about our things. We say very well it may be true. Quantum mechanics is not the whole story. There may be a better theory. Quantum mechanics is just a theory. People get very caught up on quantum physics, but it's just a theory. It's a product of our minds. There could very well be a better one. But our prediction is that if we find such a theory, it will not restore our notion of classical reality of pre-existing things having properties before we measure them. Our prediction is it will be even weirder than quantum mechanics.
Right. So we might be living in a post-quantum world of which quantum mechanics is a sort of an effective theory or some sort of limit, and that's bad enough. But we may find that we're not, as you said, not go back to the good old classical world, but something
precisely
even stranger, which may indeed have its own range of applications, just as quantum mechanics does. This gives us all this technology. There may be post-quantum technology, even more magical than quantum
technology. Could be. That's right. Yeah, the very last section of the book is what we call our speculations on a post-quantum science.
This is heartening, I'm sure, for the people tuned in, because some of them may be planning a career working at the cutting edge of quantum mechanics. Maulik, do we have any questions?
Yeah, speaking of people who have tuned in, we have a lot of questions. So I think why don't we turn to questions addressing those. So there was a question sent in by email by, I think, Barbara Temple that says, well, quite simply, why should nature care if we're looking?
Yeah, that's a very good question, and that's what philosophers have been arguing about. The simplest question is that if I do make a measurement and I calculate what the state would be if I weren't making a measurement, and I use that state to make a prediction about the future, I get the wrong answer. So my act of intervening, well, okay, so remember, I have to be a little bit careful, because quantum mechanics, as we're clear, is a probabilistic theory. It doesn't say what will happen. It predicts the odds of what happen. And so the predictions of quantum theory are probabilistic predictions, right? And so once we understand that, then we have to basically use a probabilistic schema to be able to test the predictions of the theory. And so the simplest answer is that when I do interrogate the system, those statistics change. And a great part of the advanced topics in the book is giving you advanced mathematics to precisely calculate how those probabilities change, condition on what we measure in the laboratory. So let me give you an example. So we give two kind of characteristic examples. So one is what we call the quantum dot example, and that's essentially kind of an artificial atom where electron lives in one of two puddles of a semiconductor. It can be bound in this one or that one. And we can say, how can we determine where the electron is? And the answer is that you can use the charge degree of freedom as a kind of a handle on that electron. And what you do is you send a current through a nearby quantum channel. And depending if the current takes a large value or a smaller value, you can deduce, because of the fact that the presence of electron changes the resistance of that conductor, where that electron is, okay? And so that's a particular kind of example where the presence of that measurement of being able to determine where the electron is changes the state of that electron, okay? And so being able to accurately predict the statistics of that is a part and parcel of this new quantum measurement formalism.
Great. And on the same theme, there's a question from Dana Rasmussen who asks, how do you foresee our methods of quantum measurement evolving? Specifically, could you discuss any emerging technologies or theoretical frameworks that might revolutionize our ability to measure quantum systems?
Well, this is the big story. This is the story. It is the fact that in the old days, back in Bohr and Schrödinger and Einstein, the technology for being able to measure this was quite primitive. And things have changed rapidly. So back in those days, they had these Gedanken experiments. What would happen if this or that happened, and try to dream up different scenarios. Right now, we've been able to develop the technology over the past, nearly 100 years to be able to go and directly test those questions in the laboratory. So that's been the real advance. And I'll tell you the other great advance in terms of being able to do these kind of continuous measurements I'm talking about is the development of what we call quantum limited amplifiers. So taking very weak microwave frequency electromagnetic radiation signals, putting it into amplifiers that are able to operate the quantum limit, that add the smallest amount of noise possible to this signal to amplify it up to classical levels. That kind of technological breakthrough has really given us a very precise and quantitative handle on these theories of quantum measurement. So it's really kind of both walking together. The fact that we have really rapidly advancing technology, but also really cutting edge new theories to be able to predict, this wave function collapse story, how does it actually work? We can actually now peer into that process as a dynamical process to see how that collapse happens continuously in time.
Okay, great. And Miguel Aguilar asks, how is it possible to make a partial collapse?
That's a great question. So there are many ways of doing it, but usually what happens when you have a full collapse is that you have typically a system that you're interrogating, and you have a meter degree of freedom that associates it with it. So for example, in the sort of classic Stern-Gerlach experiment, if the spin of the valence electron of the silver atom is up versus down in the basis defined by this fringing magnetic field, the atom will either be deflected up or it will be deflected down. And what you need is a strong enough magnetic field such that those two possibilities clearly split on the screen. You can tell, aha, this is the up electrons here, this is the down electrons here. That is sort of the traditional textbook collapse. But what happens if you weaken that magnetic field? If you make a very weakly fringing field, then those two things begin to blur together. And then it becomes unclear. There's ambiguity. So what can happen? Maybe I can show a picture here. Yeah, let's see if I can find a good picture. Yes. So here in this picture, oh, sorry, just a moment. No, this one. No, I did it again. All right. Well, I'll just keep it on here. Right. So in this kind of particular, you can see this upper figure here on my screen. What happens is that if there's a displacement of one of two possibilities, what happens is that if those displacements correspond, for example, to the spin up and spin down of an atom, if I measure a single event, what happens is depending on where I measure it on the screen, I don't unambiguously know if that corresponded to a spin up or spin down electron. And so what happens is that when I measure it somewhere in this gray region where I don't have perfect certainty, then what happens is that the quantum state of the particle doesn't completely collapse. So for example, the up or the down, but only slightly moves a little bit. It's a partial collapse. So that's an example of a partial collapse. The other collapse, like when I have this kind of system, is that you send in some microwave frequency light into this cavity. What happens is that there's an interaction between the light and that quantum circuit, and you take that light out and you amplify its properties. And what happens is that you're looking for some kind of phase shift of that light, and you have this ambiguity where you know only that the light may have a phase in this range or it may have a phase in that range. And so just beyond knowing the phase of that light doesn't give you perfect knowledge about what the state of that quantum system was. And we show that ambiguity causes that partial collapse, and it happens continuously in time. So you can track that partial collapse as it goes. So that's really a very new kind of thing that we've discovered quite recently in our scientific endeavors.
Another question from Barbara Temple on the topic of collapse is, do the new continuous collapse experiments rule out any interpretations of quantum mechanics or lend credence to any of them?
That's a great question too. So one of the things that we point out in the book is that one of the things we don't like about this sort of zoo of quantum interpretations is what they do is they take some phenomena that exists in nature and they try to ex post facto give some explanation for it. In other words, they have the phenomenon already and they try to then cram it into their worldview. And so I think you can do that with almost any interpretation because the human mind is very elastic and very ingenious. But I mean, our motto is the best interpretation is a fruitful interpretation. In other words, what do I mean by that? I mean, if you adopt that perspective, does it suggest new phenomena you don't know, or suggest new ways of looking at the world you wouldn't have looked at it without that? And does that lead to scientific fruitfulness, discovery, invention? This is what I think people are missing in this interpretations debate. And so our point of view, so the thing that we think is most likely going on that helps explain this is to adopt this, what we call an epistemic interpretation, that the state we assign is really not something that exists out there, but it's our assignment, it's our calculational tool that we put on the system and use it to be able to calculate things. So I think for us anyway, that has been the most helpful interpretation. But I don't think there's any kind of definitive proof or theorems that have come from this.
Okay, more on the topic of interpretation. So yours sounds a bit like shut up and calculate fruitfully or something.
No. So if I only shut up and calculate, we never discover any of this stuff, right? So I think you have to probe new and interesting questions. And this whole formalism of being able to develop this formal approach is all new stuff, right? But what we don't do is so it kind of depends on your philosophical take on this, but what we don't do is try to give some kind of ontology to the system. We don't say that there are particles and waves. We don't try to say, oh, there really do exist properties. You just don't know what they are. In fact, you can show, if you take that approach, you can show it's demonstrably wrong, right? There are theorems, this Cock and Specker type theorems, that prove that if you try to ascribe properties of the system before you measure it, you can draw contradictions.
Right. Another question on interpretations. Is it accurate to state that if the collapse of the wave function is real, then Everett's thesis and the concept of the multiverse would not be correct?
I think that's an accurate statement. Yes.
So there's genuinely a
I'm certainly not a big fan of Everett and the multiverse. I'll be direct about that. So our calculations are all one world calculations. Collapse is a thing. Although we're not like there are people that are physical collapses, like the Girardi, Remy Weber people that say there's some kind of extra physical stuff going on, little flashes that cause things to collapse. I don't think that's right either. I think what's happening, the collapse is not happening out there. The collapse is happening in here. So it's our tool, or it's our wave function we describe. We simply refine it as we gather more information, just like Bayes' theorem does.
Okay. Well, here's a kind of philosophical question. Is this simply the ongoing trend of science knocking us off our pedestal, like the Ptolemaic universe?
Science knocking who off our people
Us,
off our pedestal?
Yes.
Well, it depends on how. It depends on what interpretation. Now Wheeler was an interesting character because he had this idea of observer participant. So that as you make an observer, you bring reality into being. That property did not exist before you measured it. And so he had this idea of the universe being created by us as observers, right? And there are people that have this idea of consciousness being responsible for wave function collapse as well. I don't subscribe to that, but that's another point of view. But in terms of this knocking us off our pedestal, I think a more modest view, this view that it's simply the information in our minds, that this is not telling us something fundamental about the universe, but it's simply saying it's the way our tools need to be handled in a certain way. That's a much more modest, I think, view of quantum theory as simply a product of our minds, right? And one of the things we comment in the book is I quote my former friend, or my current friend, but former colleague, Joe Eberly, who said the wave function belongs to you, not the electron. Which is that if we try to take it too seriously, it's like giving reality to our calculational devices. We shouldn't confuse our calculations with what the reality is, if there's such a thing as quantum reality besides what we've already talked about.
Can I interject with a quick question whilst you're surveying the remaining ones, Maulik? So Andrew, you mentioned a few times about weak measurements and how this opens up a whole new field for probing what's going on in quantum systems. But you didn't tell us whether there are any useful, practical, technological applications of weak measurements. Is there a sort of weak measurement industry in the wing? Should we be investing in it now?
Well, this is actually one of my things I'm best known for, Paul. My own research, actually, I have a lot of papers in this area. So thanks for asking about that. But one of the things I think I mentioned in my presentation is that weak measurements are used for making very precise measurements of certain things. And so we have a bunch of experiments about measuring very precise optical phase shifts, beam deflections, frequencies. And one of the things I'm really excited about is that we have a relatively new paper that's doing this all on integrated optical chips. So you have little tiny chips about the size of your thumbnail, and all of the interferometry of the light is on the chip. And so you can build weak value type devices where you get this amplification effect that I've been talking about with post-selection. Well, I don't want to go into the details of that. But you can do it on chip, and we have very nice measurements of optical frequency, optical phase, and we're starting to build optical gyroscopes with these as well. So that's something that I think is quite exciting and something that we're working on. The other application I mentioned, not necessarily of the weak value type measurements, but of the continuous quantum measurements, is this continuous quantum error corrections. We published a paper with Irfan Siddiqi, the very first implementation of doing quantum error correction continuously, not as a gate-based type operation, but to be able to monitor the systems all the time to see is there an error that's creeped in? And once there is, aha, I found it, I can then correct it. So that's another example. But there are other examples that we talk about in the book. And one of the other exciting ones I didn't talk about in my presentation, but we go into some length is being able to create entanglement at a distance by measuring some joint property of the system. And one of the things I do think is very important in terms of quantum technology is building a reliable quantum link that keeps two things entangled indefinitely without degrading over time. And we've been able to find a way of doing that using only local operations. And that's something that I'm quite excited about.
And that's involving some sort of weak, if not measurement,
it's essentially continuously monitoring the spontaneous emission of the two atoms. So the protocol is you have two atoms, and you're able to take their emission, the light that it would emit, and put it into a waveguide, and take that light and then measure it with some other light that you combine with it. And by monitoring those signals and also driving, if it turns out you have to drive the two qubits independently, you can then do feedback on the local controls to be able to maintain that entanglement link, even in the presence of this relaxation, spontaneous emission type effects.
Right. Well, shut up and calculate. Well, I better shut up and listen, because I'm sure Maulik has more questions from our viewers.
Yeah, we have more questions about applications since we're on that topic. Jay Vicker asks, how does quantum measurement apply to the development of quantum computers?
Yeah, that's a great question. So it's funny because all quantum computational algorithms have three steps. They have a preparation step, and usually they're gate-based. So then they have a bunch of qubits that are the logical carriers of information. Then there is the algorithm, which is a bunch of unitary operations. And then at the end, there's a little box that says measure. And for the quantum computing guys, it's just a black box. You just project your wave function, you get some results, and then you do your computer science with that. But how you do that is really important, right? And so being able to build a technology to do that efficiently without false positives, that's really hard. And so that's something that we've been working on extensively, and people around the world have been working on extensively. So that's a huge component of quantum computing, is high fidelity measurements. And in terms of these continuous measurements, there's another part they don't talk about so much, because all you need there is you need somehow these histograms to get well separated. But for these really these measurements that test the sort of foundations of quantum mechanics, you need more. You need really high efficiency quantum measurements, so stuff that doesn't lose information. So as you measure it, what happens is that typically that you scramble your system, you're partially collapsing it. But if you lose information, you also dephase it. There's also decoherence as well. And so that's sort of the trash you don't want. And so being able to build the detectors that don't lose information, that are very efficient, is really hard, but also really important for these tests of quantum mechanics.
So here's a question that combines all the hot topics today. So how could quantum technology make artificial intelligence more efficient?
You know, I've gotten this question a lot these days. And the simple question is, I don't know enough about artificial intelligence to have an educated answer. So there's an important phrase from antiquity: know thyself. Don't say stupid things about things you don't know. So I suspect there's something interesting to be had there. I will say one thing that we have been doing is using either artificial intelligence or machine learning to be able to develop new kinds of quantum gates. So that's one of the things I do for a living, is with Irfan and colleagues, we have a big grant from the Army to build quantum computing gates. And one of the things you have to do is you have to apply these time-dependent pulses on your qubits to make a really high fidelity gate in a really short amount of time. And so we're starting to use some of these machine learning techniques to try to optimize some properties of that. If you change the envelope, can you get better efficiency? But there's a whole other possibility of making AI quantum, which I really don't have anything to say about.
Okay. David Boone wants to know, can quantum vacuum fluctuations be measured? If so this is about quantum field.
Oh, yes. Quantum vacuum fluctuation. Yes. They're really important. They were really important. So remember I told you about quantum amplifiers and the fact that I can't amplify without adding noise? The reason you add noise is because of the quantum vacuum. So that noise comes from the quantum vacuum. But one of the things I'm really excited about is that we've been and sort of going back to my 4 interests I was talking about at the beginning of the talk. My last interest there is sort of combining foundations of quantum mechanics with thermodynamics. We have a really interesting paper recently that I call the quantum vacuum fluctuation engine. And it's something I'm really excited about. And I can explain to you very simply how it works. The idea is you take a chain of these qubits, or it could be oscillators or whatever system you want, and you let them interact, and you leave them alone. You let them go down into their ground state. And then one of the things you learn about the ground state of these interacting systems is it's an entangled state. So I can't describe it without talking about the properties of all the systems together. There's correlations among all of the systems. And the protocol to make the quantum engine is you come along and measure just the energy of the system itself, not the coupling energy. It is a Hermitian operator, so it's a valid thing you could measure in quantum mechanics, and you do it for all the systems. And one of the interesting things is because this is an entangled state, that means that when you measure each of these systems, I don't just get the ground state of each system individually. Sometimes I get the excited state of that system. And that excited state is actually a resource. So I can come along and then I can extract that energy, take it back down to the local ground state, pull that energy out, I store it, and then let the thing relax back to its ground state, and I repeat the process over and over and over again. And this creates an engine cycle. So that's the thing that not only is the vacuum fluctuation real, it's actually the source of my engine cycle. Now you could say, oh my gosh, Andrew, does that mean I can extract energy for free from the vacuum? And this is something that people get very excited about. Alas, no, that's not the way it works, because to do the measurement, this is something else people didn't really realize until recently. To do the measurement takes resources. You have to have energy to do the measurement. And that's something you don't learn about in your quantum mechanics textbooks. So when you take that energy into account, that's like the fuel that drives the engine. And you know that anytime you have an engine, you put the fuel in, the work you get out has to be less than the work you put in. Otherwise, you violate perpetual motion machines. And so that's what happens there, is that it turns out the work you put in to do the measurement has to be bigger than the energy you get out. But nevertheless, it's still an engine cycle. And you can calculate efficiency and things like that.
Great. We're almost out of time. I think we have time for one last question. And so here's a kind of suitably philosophical question for the end. So you mentioned briefly about a post-quantum theory. So Edwin Ugas, if I'm pronouncing it correctly, wants to know, do you think quantum mechanics today, as it stands, is just a piece of a more complete theory like electricity and magnetism were?
Almost certainly. Almost certainly. Yeah. And what we're very clear about at the end is that there are vexing issues that remain, that have been plaguing us for all. We know a lot more than the founders did, but there are still a lot we don't know. And so I think in our prediction is to have a seamless theory where there is kind of a theory that describes all domains. We're going to have to go beyond quantum mechanics. I think quantum mechanics simply doesn't have the ability to answer those questions. So that's our prediction.
So where would you say is sort of the direction in which you could modify the foundations of quantum mechanics?
Well, I think it has to. I think tinkering won't work. I don't think you can say replace Hilbert space by some other space or replace states by some complex space cats or something. I think it needs to be completely redone. So I don't know. If I did, I would be ecstatic, but maybe that's something for the future.
Do you think that's going to be necessitated by quantum gravity, or is it that our existing theories are in some sense defective? Even without discussing quantum gravity, are you saying that the theories we have, besides the interpretational issues, are somehow not satisfactory?
Well, look, let me be clear. So what we say is, from the point of view of predicting the correct statistics of events that we have seen, quantum mechanics is a perfectly adequate theory. We don't see any deviations from quantum predictions from what we've seen so far. Right? It could well be, though, for example, when we're building this quantum computer, and we say that in some sense the quantum computer is the ultimate test of quantum mechanics, because you have to build this massively parallelized quantum object that is making massive use of entanglement, coherence, everything, it could be something breaks, right? And this shows the limit, the boundary of our theory. And it wouldn't be so different than what happened at the beginning of this past century, when we started trying to probe blackbody radiation using classical physics and realized something breaks, and then we have to do something new. What that new is, I don't know. But I very much doubt that quantum mechanics, as it currently stands, is the defining end-all be-all theory.
Great. On that note, I think we should all get back to work and figure out how to improve quantum mechanics. Thank you so much, Andrew, for that fantastic and stimulating discussion and presentation. And have a nice evening wherever you are to our participants, and we'll see you next month. Bye-bye.